Hi, welcome to chemistry class, and I am Odisola Lekan Adiola, your chemistry teacher. This video is brought to you by Igota Virtual Learning. In this video today, we are going to be looking at electronic configuration or electron configuration. We will look at what electronic configuration is. We will look at the rules that guide electronic configuration of elements, and of course we'll look at some of how we can write the electronic configuration of these elements in terms of the shell notation, the subshell notations, and some other rules that guide them. Of course, we are going to be solving questions involving electronic configuration, basically wire question. So welcome to class. Let's start with what the electron configuration means. The electron configuration describes how electrons are distributed or arranged in various um, atomic orbitals. We can also say electronic configuration is the arrangement of electrons around the nucleus of an atom. In particular nature of matter, you learned about the subatomic particles, where you have the nucleus at the center of the atom and surrounded by um, electrons. And of course, these electrons are found in orbits, and of course they are attracted to the nucleus. So there is a way by which we arrange these electrons around the nucleus of an atom, or how these electrons are distributed around the nucleus of an atom. So from here we could see that uh, um, electrons can be arranged to show, number one, the principal quantum number. For instance, the gas state electron configuration of hydrogen that we put here. You can have the number of electron in the orbital or the subshell. You can show the arrow that shows the spin, either positive or negative, and then you can show the energy level, as the case may be. As we progress in this course, we are going to be looking at that. So basically, electron configuration describe how electrons are distributed in various atomic orbitals, or we can define as the arrangement of electrons around the nucleus of an atom. Now, having said that, there are two basic ways by which we write electronic configurations. Although we have the third way, which will be discussed later on, just as an addition to this video. Basically, we have the SPDF notation. The SPDF notation is a subshell notation, and of course, S means sharp, P means principal, D means diffuse, and F means fundamental. They are subshell notation. For instance, the number there, which is 1 from this diagram or from this picture, means the energy level, the value of energy level. So this here is energy level 1. The one at the subscript means the number of electrons. So the number of electrons that hydrogen has here is 1. And then the third one, which is S in green, means the sublevel, the S sublevel. So we can have it as 1s1. That's is SPDF notation. Then we have the orbital box notation. Now, in the orbital box notation, if you are writing for helium, for instance, the box will indicate this electron spin, whether it is clockwise or anti-clockwise. So we have, in that box, you have the helium is 1s2. Therefore, we can have one of the electrons going up and the other going down, showing they are spinning in opposite direction. Okay, having said that, like we have discussed, we have the SPDF, which are the subshell, and then they have their shape. For instance, S is spherical, like a ball or that is round. So S orbital is always spherical. That's the shape. The P orbital is dumbbell. The P orbital is dumbbell. That's the shape. The D orbital is double dumbbell. The D orbital is double dumbbell. The F has a complex shape, and that's why we are not putting it here. So the shape of these orbitals or this subshell are S to be spherical. Of course, we have said S spherical, P um, dumbbell, D double dumbbell, and F complex. Also know that when it comes to this orbital box, S has a maximum of 2, P has a maximum of 6 electrons that it can contain, D has 10, and F has 14 maximum number of electrons they can contain. Okay, so there are 3 rules that guides electron configurations. There are 3 rules that guides electron configuration. We have the Aufbau's principle, we have the Pauli's exclusion principle, and the Ohm's rule. These are the 3 rules that guide electron configurations. Let's look at them one after the other. For the Aufbau principle, it states that electrons enter the lowest energy orbital first. And the instruction is when you are writing the electronic configuration following the Aufbau's principle, you fill the lower energy orbital first. So another way to put the Aufbau's principle is you can say in the building up of atom, electrons are fed into atomic orbital with lower energy first, and each orbital may hold up to 2 electrons. In the building up of atom, electrons are fed into atomic orbital with lowest energy first, and each orbital may hold up to 2 electrons. This principle explains that no lower level will be vacant when a higher level or sub-level accommodate electrons. That means that a building up of electrons in an atom is systematic. Building up of electrons in an atom is systematic. So that means the lower the principal quantum number, the lower the energy. So within an energy level, S orbital at the lowest, followed by P, followed by D, then F. So F orbitals are usually the highest energy for that level. So that means that if you are feeling, according to the picture we are showing you there now, if you are feeling the energy, you start with 1s. After the 1s, you go to 2s. After 2s, you have 2p. After 2p, that's 3x. 3s, you will observe that 1s has maximum of 2, 2s have maximum of 2, 2p has 3 lines. That means 2, 2 each. Don't forget we have said that the maximum number p can contain is 6. So you have 2, 2, 2. Then we have 3s, which can also have 2. We have 3p, you can have maximum of 6. You have 4s, 2. Then we have 3d. 3d can contain up to 10. Of course, d orbital can contain up to 10. So you have 2, 2, 2. That's why we are having 5, and so on. So Aufbau's is saying that we fill the lower energy first before we fill others. That's generally the summary of the Aufbau's principle. Okay, now the next rule we look at is the Pauli's exclusion principle. And the summary of Pauli's exclusion principle is that no more than 2 electrons in any orbital. So it states that an atomic orbital may have up to 2 electrons and then it is full. An atomic orbital may have up to 2 electrons and then it is full. To also say that, we can put it this way, we can say the Pauli's exclusion principle states that no 2 electrons in the same atom can have the same values for all the 4 quantum numbers. no two electrons in the same atom can have the same value for all the four quantum numbers. So what does this mean? That means that the spins have to be paired. It means that we usually represent this with an up arrow and a down arrow. And then since we have only one s orbital per energy level, only two electrons can fill that orbital. So what is Paulis saying generally? Paulis is helping us to ensure that we have to fill, we can pair the spin. Once one go up, the other comes down. That means we cannot have two in a particular orbital going up at the same time. One must go up and the other must face the opposite direction. That is what Paulis is trying to say. Then the next one is the Ohm's rule of a maximum multiplicity. The Ohm's rule of maximum multiplicity. It says that when you get to degenerate orbitals, you fill them all halfway first, and then you start pairing them up. Or we can say that electrons are distributed among the orbitals of the same subshell singly before pairing. Singly before pairing. So what do we mean by saying degenerate orbitals? Degenerate orbital means that they have the same energy level. For instance, 1s, you have the 2s and the 2p. They are degenerate. You have the p degenerate. So we have 2p orbitals on each level are degenerate. The 2p orbitals on each level are degenerate. So they all have the same energy level. 2p have the same energy level uh, um, to one another. Then the d and f orbitals are also degenerate. They also have their own degenerate too. So from the diagram here, you could see for Ohm's rule, carbon, for instance, we'll get to that very soon, has electronic configuration 1s2, 2s2, 2p2. And then if you are filling up, you have the 1s2, the 2s2 there, and then the 2p. But when it now comes to nitrogen, you observe that you have 1s2, 2s2, 2p3. So you have to feed them singly first, according to one of these theories that we have mentioned about. You feed them singly. Then once you feed them singly, then you double the opposite direction spin. But it's interesting that you have 2p3. That means you have to feed them singly. That's 2p3, filling them up. By the time you get to oxygen, for instance, you have oxygen to be 2p4, 1s2, 2s2, 2p4. You feed them singly first, it will remain 1. Then you come back to pair them. So then when you are pairing now, one is facing up, the other is facing down. Since 2p are degenerate, the Ohm's rule applies in that direction. So let's quickly look at the summary of the rules or the principles that govern them. Let's take from hydrogen to neon. You observe that the electronic configuration of Z mean here the atomic number, the atom is hydrogen, configuration and orbital diagram. So let's look at them. Hydrogen is 1s1. Hydrogen is 1s1. So we feel it as 1s there. Now it's going up. By the time you get to helium, you have 1s2. It's still the maximum s can contain is 2, so we can still fill up the 1s2 orbital there. By the time you get to lithium, you have 1s2, 2s1, 1s2, 2s1. Now this takes us back to, you will notice that we highlighted here about half bars. This particular one take up about half bars. So let's look at the half bars again that talk about we feed the energy lower energy orbital first before we feed the higher one. So here in this you will observe that we filled the 1s first. So we make sure that the 1s is filled, that is having 2, before we go to the next one, which is 2s, and 2s is higher than 1s. So you fill the 1s first, 1s you fill it up, then the last one, which is 2s1, you then fill it up. So this fulfill the Avbau's principle. By the time you get to carbon, we can talk about Ohm's rule. We can talk about Ohm's rule that you feel singly before you pair. For instance, let's look at carbon, nitrogen, and oxygen. Carbon is 1s2, 2s2, 2p2. So you feel 1s2, you feel 2s2, then the 2p. In this case, you don't feel it, the first box that is here now. You don't feel it as 2p2 there, because 2p is having three orbitals. Each orbitals can take maximum of 2. Is having 3. So therefore, you have to feed them singly first. 1 1. That means it's having an empty 1. By the time you get to nitrogen, for instance, which is 2p3, you are going to feel 1 1 1. That means that is showing the 2p3. We are feeling it. We are feeling it singly. By the time you get to oxygen, where you have 2p4, so you are going to feel singly before pairing. That means in 2p4 now you have 1 2 3 remaining 1. You now go back to the first one of the 2p to feel the second one, and then when you are feeling, it is we are feeling, if one is going up, the other must come down, based on the Pauli's exclusion principle, that they must not have the same direction. One must go up and the other must go down. So this diagram explain the three principles in details. Okay, so let's look at how the step that it needs for us to write the electronic configuration. Step 1, in writing the electronic configuration, you determine the atomic number of the element from the periodic table. This will give you the number of proton and the number of electrons in that atom. For instance, magnesium. Magnesium is in group 2 of the periodic table, and then of course the atomic number is 12. So therefore, if it is 12, atomic number is the number of proton and electron. That means magnesium will have 12 protons and 12 electrons. Okay, so in writing for magnesium now, we can draw 9 boxes to represent the 3 energy levels. Don't forget that magnesium, since it's having atomic number 12, and is in the periodic table group 3, group 2, which have the S and P, and of course is in period 3, of the periodic table. So we have to represent using 3 energy level, is in period 3. So you have one for 1s, another one for 2s, we have for 2p, we have for 3s, then we have for 3p. So once you draw it like that, now we begin to fill. We add them one by one. We add, for instance, if you are writing for magnesium, you want to say magnesium is 1s2, 1s2. So you fill the 1s first, which is 1s2. That means since it's 2 electrons, one must face up and one must face down. According to the Pauli's exclusion principle, one must face up, down. Then the next one, you feel the next orbital, which is 2s. You have your 2s2. You have your 2s2. One is going up and the other is going down. By the time you get to 2p, because it's having 2p6, magnesium is 1s2, 2s2, 2p6, 3s2. By the time you are filling for 2p, you know we are having 3 boxes. The first thing you do, you fill them singly, all of them facing one direction. 1 2 3. You are now left with 3. You now come back to pair, and those ones will be facing down. 1 2 3, making 6. 2p6, you are left with 3s2. That's 2 electron, one facing up, one facing down. Magnesium do not have any 3p. Magnesium do not have any 3p because it's only 12. So that's how you write it. So therefore, finally you have 1s2, 2s2, 2p6, and 3s2 as the configuration. Please let me go back to this number 3. Um, don't forget, you add one electron each into each box in a set, then you pair. Like 1s is a set of a box. Generally, you add one pair. 2s is another set, one pair. 2p is another set, 1 1 1. Then you pair 1 1 1, making 6. 3s is another box, 1. Then you pair. Don't forget. And then of course it gives us 1s2, 2s2, 2p6, 3s2. Okay, now we can do that one for all other for hydrogen. We could see from here you have, for hydrogen you have 1s1, helium 1s2, lithium 1s2, 2s1, beryllium 1s2, 2s2, and so on up till um, about scandium, titanium, and the like. So you can have it like this. Plus, please note that all the numbers in the electronic configuration add up to the atomic number of that element. That means that all the number, for instance, hydrogen is 1, helium is 2. Now when you go to sodium, where you have 2 plus 2, sodium is having 2 plus 2 plus 6 plus 1. 2 plus 2 plus 6 making 11. So the atomic number of sodium is 11. The same thing for all other ones that are here. Let me encourage you to uh, write the orbital notation for each of these electronic configuration that you see here. Please write it and practice. Let's see what you are going to get. Ensure you practice it in that line. Okay. Now, one last thing that you need to know. If you look at the previous slide, look at hydrogen, lithium, sodium, and potassium. Did you see any similarity? The similarities you are going to see there, in hydrogen has 1, is ending with 1. Lithium is also ending with 1, 1s to 2s1. Sodium is ending with also 1, 3s1. Potassium is ending with also 1, 4s1. So they are ending with s1 each. That means they belong to group 1a, because they have similar ending, each of them. That means they have one valence electron in the outermost shell. So we can use that one to determine, to place elements in groups and periods respect in groups generally. Their valence electron are used to place them in groups. So since they're having one valence electron, that means one electron at the outermost shell, they are group 1a elements. Okay, so we can look at them now. Like we have said, they are ending with 1. So the similar configuration they have will cause them to behave in the same way or in a similar way chemically, because they are in the same group. And they are in the same group because they have the same valence electron, which is 1. And then because of this, they are going to be in the same family. For instance, this is their group 1. They are called the alkali metals. uh, um, because each group now we have the same configuration, and then they are going to end with S1. So let's take note of that. We can also take note of this. For instance, um, elements within a given family have similar configuration. That's what we are trying to say. For instance, this is another family, uh, the noble gases, group 8. They have uh, 8 or 2. They have the octet or the duplet structure. um, Duplet for helium, while others are having the octet. That's 2 plus 6 8, 2 plus 6 8, 2 plus 6 8. So they're having 8 8 8, and then that's octet. Then helium is 2, that's duplet. So these are the noble gases. The same thing, the alkaline earth metals, you will see beryllium ending with 2, magnesium ending with 2, calcium is also ending with 2. That means they belong to group 2, called the alkali earth metals. So you can practice with this again. Make sure you write the orbital notation for this. practice, then also determine their atomic number. From this, practice write the fill them in orbital bars, and of course write determine their atomic numbers. Also practice with this. I want to see, let's see whether you are going to get it or not. Okay, we can also discuss electronic configuration and the periodic table. This is a sample of the periodic table where you have um, the 1s, the 2s, the 2p's, and the like. You observe something here. We have, this is when you are going like this in terms of going sideways from left to right, you are talking about the period. And then when you are going from up to down, you are talking about the groups. You observe that you have uh, the group 1, group 2. In between group 1 and group 2, you have some group called the transition elements. They are in D, 3D, 4D, 5D, 6D. The transition elements. Then you have group 3, 4, 5, 6, 7, and 8. Then when you now go to, you have the ones that are in F. They are called the Latinites and the Actinides. The Latinites and the Actinides. So those are the F block elements. So we have the X block elements. We have the P block elements. The S block elements are group 1 and group 2. The P block elements are group 3 to group 8. The D block are in between. They are called transition metal. They are the D block elements. And then we have the F block element, which has the Latinites and the Actinides. Okay. So let's look at how we can write shorthand electron configuration. If you are writing shorthand electronic configuration, that means you want to shorten it. Instead of writing, for instance, the ones that are very long, when you are dealing with atomic number of 58, 72, and the likes, and then or you are even dealing with 21, and then you don't want to stress yourself too much, we usually take those of the noble gases. We can use argon, and then we can use neon, especially. For instance, if it's between element 1 to 10 or thereabout, or even element 1 to 20, you can use them. For instance, argon has, if you are writing for element 1 to 20, you use neon. Then if you are writing 21 and above, you can use argon. For instance, argon itself is atomic number 18. So if you want to shorten it, you can put neon in bracket like we are seeing here. This neon is showing that you have 10 already, so you need 8 more. So neon in bracket 3s2 3p6. If neon is 10, then 2 plus 6 will give you 8, plus this 10 making 18, since argon is 18. Now go back to configuration of argon itself. Argon has 1s2, 2s2, 2p6, 3s2, and 3p6. And since you know that 1s2, 2s2, 2p6 makes 10, 2 plus 2 plus 6 makes 10, we can cut that one off and put neon there. So we are now left with 3s2 and 3p6. So to shorten the configuration of argon, we can say neon in bracket 3s2 3p6. So we have shortened that configuration. So we can do that for a whole lot of elements as well. For instance, we can even use it for transition elements. But when we get to element 21, which are the transition element, and we want to shorten them, we are going to be using argon, because argon is 18, for instance. Chromium has atomic number of 24. So if you are writing, we are going to write argon 4s1 3d5, and not argon 4s2 and 3d4 as expected. These are exceptions. We are going to talk about them very soon. So for copper, which is 29, you are writing argon 4s1 3d10. Now the discrepancies here is or the anomalies that we experience here is because the D subshell is a bit stable and more is higher in power or in energy than the 4s. The 3d orbitals or d orbitals, when the 3d orbital is greater in energy, the 3d orbital is greater in energy than the 4s, and that's why we are writing the 4s before the 3d. So as such, um, uh, at some point they are either half filled or completely filled. Uh, in the case of chromium and copper, uh, they are either half filled or completely filled. That means the d orbital. So that's why we are putting chromium as 4s1 3d5, ensuring that the 3d is half filled. In the case of copper, that's why we are having 4s1 3d10, making sure the d orbital is completely filled, because the d orbitals are slightly greater, they have slightly greater stability, and are usually half filled or completely filled. Okay, now you can see a whole lot of writing that we have talked about. For instance, look at copper. So if you are writing for copper, for instance, I think we have written for, this is chromium now. If you are writing for chromium, you are having 4s1 and the 3d5. Yeah, 4s1 3d5. You can see 4s1. Argon, 4s1 3d5. Argon means 18. Then if you count the other, 18 plus 1 2 3 4 5 6 will give you 24. 4s1 3d5. They are written singly, and because none is left, you cannot pair. Now when you come back to copper, which is 29, 18 plus 11, because you have 4s1 3d10 singly, there you pair, so you are going to have 3d10 here and 4s1. So this is how to write the both of them. Okay, you too can also try and write the shorthand notation practice for aluminum, calcium, nickel, iodine, and astatine. Kindly do that now as you watch this video. Kindly do that. Okay, if you have done that, check if you are correct. Check if you are correct. Check if you are correct. For aluminum, the normal configuration is that, and of course the shorthand configuration is written below, and the same for others. Now you observe that immediately we finished with nickel, we are not using argon as the shorthand again. We are using krypton. Now we use neon, we use argon, we use krypton, and then we use xenon as our reference. Now once is between 21 to 30, we use argon. Once we get to 31 to 40, then we begin to use krypton, and that's why you have 21 31 to about 50. Iodine is about 53, and that's why we are using krypton here. And then the same thing, the higher ones, we use xenon for them. Okay, so you can also do your own by practicing these ones. Take time to also practice this one and provide the answer. Take time to practice and provide the answer. Okay, now uh, let's look at the shell and the subshell. There are no major differences for the shell. For the shell orbital, which is the energy level of the orbit, you can where we have the k element shell. We have, like I've said the other time, we have the shell and we have the subshell. Shell is the energy level or orbit, while subshell is sub energy level. And the circular part that electrons take around the nucleus is known as the shell or the orbit, while the subshell is a shell or energy level that is subdivided. Now each shell is represented by a value n, and then each subshell is represented by a value l. N is 1 2 3, L start from 0. That's another difference. Then you have in shell we are using KLMNO. In subshell we are using SPDF. And then there is a general formula for the shell, which is 2n squared, and that means the maximum number of electron K can contain is 2. The ones that L can contain is 8, M can contain 18, and then N can contain 32. But for subshell, we just have the value to be N. S can contain 2, P 6, D 10, and F 14. So this is a major difference between the shell and the subshell notation. Okay, so just as an introduction or as an addition to this, if you are writing the shell, as an addition to if you are writing the shell notation, this is how you write it. The configuration will be 1 2 2 1 2 2 analyze. This is up to Lagon. You can do others yourself. And then if you are writing it for shell notation, if you are doing the diagram, chlorine is, for instance, now you can see chlorine is 287, and then that means it is 1s2, 2s2, 2p6, 3s2, and 3p5. That's 287. From here you can see chlorine is 287. If you are writing the subshell, that's 1s2, 2s2, 2p6, 3s2, 3p5. So if you want to draw the diagram for the shell, the number the 2 come first, 2, 8, and 7. 2, 8, and 7. So you can take time to also practice those ones. Okay, so let's quickly take some few wire questions before we end the class. Let's take some few wire questions before you end the class. Okay, let's look at this question. This is WAEC 2009 question 4b. WAEC 2009 question 4b. The following table shows the electronic configuration of two elements Y and Z. You have the configuration. From here, from this configuration, you should be able to determine what element they are talking about. How do you do that? We can look at some of the things I've said before and go back and determine the elements they are talking about. And they ask questions on them. The group that that Y belongs to, the period that Z belongs to, number of protons present in Z, how many unpaired electrons in Y. Then you have to write the formula of the compound formed between Y and Z. Okay, I hope you'll be able to do this. Quickly check and see if you can do it. Try and see, pause the video and do it. Okay, let's look at the similarity. You see that you have 1s2, 2s2, 2p5. If you add all the electrons together, you are going to get 9. And then that will be the atomic number. And the one that have the atomic number like that is fluorine. So they are talking about fluorine. So the fluorine is Y there. And then they ask you to name the group that it belongs to, which is what? Group 7. Which is group 7. Now they also mention Z. The Z there, they said it contains 1s2, 2s2, 2p6, 3s1. If you add them together, you're going to get 11. That means the atomic number of Z is 11. And the ones that has it is sodium. Sodium has that electronic configuration. That means Y is fluorine, Z is sodium. And then the group that Y belongs to is group 7. While Z belongs to PO3, which is sodium. Sodium belongs to PO3, while fluorine belongs to group 7. Then the other question you ask is the number of protons that is present in Z. 11 protons are present, since 11 is the atomic number. And then we have said the atomic number is the number of proton or electron. So therefore, the number of protons present in Z is 11. Now for Y, they're asking the number of unpaired electron. How do you determine the number of the unpaired electron? You can quickly go back to the electronic configuration that we discussed. The electronic configuration I want to show you. So it's important that you know all of these things. Let's take fluorine, for instance. Okay, look at it. We want to check. The configuration. Okay, see it now. Now look at fluorine. 1s2, 2s2, 2p5. That means you are drawing the 1s2, you are drawing the 2s2, and you are drawing the 2p. Okay, so when you are drawing them like that, you fill the 1s2, the 2s2, and then we are talking about 2p5. You fill them singly first, as in here. You fill it singly, then before you now double. When you double, when you fill it singly, you have 3, remaining extra of 2. You now fill the 2 with the first bus and the second bus. So that means you have one that is left that is not being paired. So fluorine generally will now have one unpaired electron. It's going to have one unpaired. That's the number of unpaired electron that's fluorine out, and that's what. So to answer the question effectively, this how you answer the question as being given. You can write the electronic configuration, and first of all tell them that the Y is element Y is fluorine, Z is sodium. Okay, so that, and then of course, to show that it has one unpaired electron, you have to draw the orbital notation. Show the of course, when you are drawing the orbital notation, you are writing fluorine. At the bottom you are putting 9, showing that it has atomic number 9. Then you now draw your box, and then you fill it in. Then by the time you fill it in, you now show from the box, you show that it has one unpaired electron. And then what will be the formula of the compound that fluorine and sodium will form? Sodium and fluorine will form NaF, sodium fluoride. Why? Because sodium will lose one electron to become 2,8. Fluorine will gain one electron to become 2,8. So that means they are forming an electrovalent compound, and that they will have ZY, sodium fluoride. Okay, so quickly let's look at another one. This is an objective question, WAEC 2012. The question says, which of the following configuration represent that of an electron in its ground state? The answer is quite simple, and is option D. Is option D there, which is 1s2, 2s2, 2p6, 3x0. That's the option D there. 1s2, 2s2, 2p6, 3x0. Now, why is it in a ground state? The ground state of an electron, when you see the energy level usually occupy is the energy level is usually the lowest state of that electron. For what are we trying to say in essence? In essence, is that the valence electron usually show the lowest energy level, and that means since we are having 3s0, that means the lowest energy for that electron or the ground state for that atom is that 0, which is and when it's at 0, it's at the ground state. When it's at 0, so easily D is the answer. Another objective question here, you have WAEC 2012 again. They say, which of the following ions has an electronic configuration that is different from the other? Now, when you have elements or atom bearing charges, these ones have become ions because ions are atom carrying charges. Now, these ones are carrying charges. They will have the same number of proton when they are carrying charges like this, but will have different electron number. Why? Because these charges is showing that they have either lose electron or gain electron. When they have negative, that means they have gained electron. When they have positive, that means they have lost electron. For instance, chlorine has gained 1 electron, oxygen has gained 2 electron, magnesium have lost 2 electron, aluminum has lost 2 electron. Now, what's the implication? Chlorine is supposed to be 287, like we have done in the shell orbital, 287. So that means that if it has gained one electron, it become 288. Or we can put it as, that means it has become 18. It was supposed to be 17, because at ground state, which it has before we become ion, the proton is 17, the electron is 17. Immediately it gains one electron, the proton is now 17 and the electron is now 18. And if you are dividing that, you have 288. For oxygen, is gaining 2 more electron. That means instead of becoming 8, it is now 10. And to divide that, you have 2 8. Magnesium is losing 2 electrons. Instead of being 12, it's becoming 10. That means it has 10 electrons. Don't forget now, chlorine is having 18 electrons. Oxygen is having 10 electrons. So chlorine is having 17 proton, 18 electron. Oxygen is having 8 proton and then 10 electron. Magnesium is having 12 proton but 10 electron. Why? Because you are having 2 plus here. That means it has lost 2 electron. While aluminum is having 13 proton and 10 electron, because it has lost 3. So out of them, which one is odd? Which is chlorine. Chlorine is the one having 18 electrons. Others are having 10 electrons each. So the answer is A. Okay, and then we could quickly look at WAEC 2005. The question said the electronic configuration of atoms of elements A, B, C, D are 1s2, 2s2, 2p2, 1s2, 2s1, 1s2, 2s2, 2p1, and 1s2, 2s2. When you see something like this, the first thing you look at is what element are they talking about. For instance, this A, 1s2, 2s2, 2p2 will give you carbon, because the atomic number is 6. If you add them together, 2 plus 2 plus 2, 6, and carbon has 6 atomic number. The second one is having 3 atomic number. Atomic number is 3. That's lithium. The third one is having 1s2, 2s2, 2p1. That's 5, and 5 is boron. And then we have 1s2, 2s2. If you add them together, that's 4. That's beryllium. So you have carbon, lithium, boron, and beryllium. So those are the elements. So if they now ask you to arrange in terms of increasing atomic size, for instance, the arrangement is as the one that has the largest atomic size is the B, which is lithium. Why? Because atomic size decreases across the period. These elements are coming. You are having beryllium, boron, carbon, lithium, beryllium, boron, carbon in that period 2 of the periodic table. So as you are moving across the period, the atomic size will decrease due to the shrinking of the shell. And the shrinking of the shell, we call it the shielding, or the shielding effect, is the shrinking of the shell rather is as a result of the effective nuclear charge. More electrons are coming without increase in number of shell. So there will be the attraction of the nucleus to the electrons that are coming will be greater, and as a result, the shell will be shrinking. So sizes decreases across the period, and these elements are across the period. That means the one that is lithium, it will be bigger in size than that of beryllium. Beryllium will be bigger than that of boron, and boron will be bigger than that of carbon. So therefore, we have A less than C less than B, D less than B. And then the other question talked about the element that is divalent. When you say something is divalent, that means it has 2 valence electron, and the ones that have 2 valence electron are the group 2, because they are going to react with S2, like we have said. So the one that is divalent is D, which is the beryllium. The one that contains 2 unpaired electrons is A, and that A is carbon. You take your configuration again, the orbital box, you take them again. If you are putting the data bus, you are doing 1s2, 2s2, 2p2. In your 2p, you are having three boxes. So if you are going to put that, you put one, you put two, the other will be empty, and the two others will not be paired. They will be they will be single. Therefore, carbon, which is A, has two unpaired electrons. And then the one that readily loses one electron will be B, which is lithium. Why? Because it has S1 as the configuration, and it's a metal, so they lose electron easily. To lose that one easily, to have a duplet structure. And then the last one that belongs to group 3 is C, which is boron. Boron is in group 3. Since they have the same energy level, 2 plus 1, 3. So you're going to use in group 3 of the periodic table. So far, this is what electronic configuration is all about. You can take more questions. So we have looked at what electronic configuration is. We have looked at the rules that guides the how to write electronic configuration. We have also seen how we can write electronic configuration, most especially the subshell, the SPDF, and the orbital notation. And then I've also shipped in how you can write the shell notation, which is the key element, how you can write that, and how you can draw them. And then we have also looked at some differences between two of them and some exercises. I hope you have learned massively from this lecture. Take time to solve past questions more on this electronic configuration. Keep on learning chemistry, and bye bye.